power functions. They don't get more powerful than this. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are taking a look at what happens when we raise x to anything. Power functions are functions which are based around powers of x that are both constant and real. Now, this sounds a lot like polynomials, except polynomials are restricted to whole number values of powers of x. So x to the first, or x to the 15th, or x to the 137th. But power functions could be any constant real number. So for instance, x to the 1/3 power, or x to the -1 power, or x to the pi power. Power functions take on a form that looks like this. F of x is equal to a times x to the p power, where p is a constant real number and k is not equal to 0. Now, we can see from this that polynomials are just strings of power functions. But now, because p can be any constant real number, we can make a whole lot more different sorts of functions with power functions. Power functions fall into a few broad categories based on what that power p is. If p is positive and an integer, otherwise known as a whole number, then it looks a whole lot like a polynomial, or a monomial version of polynomials. Because of this, if p is even, the function is an even function. It is symmetric across the y-axis. And if p is odd, then the function has odd symmetry. It is symmetric across the origin. If p is negative and an integer, then we get our reciprocal functions like 1/x or 1/x squared. Now, these functions have their own special properties. For instance, all of these functions have a vertical asymptote at x is equal to 0. They also have horizontal asymptotes at y is equal to 0. Again, if that p-value is odd, then the function has odd symmetry. It is symmetric across the origin. And if p is even, then the function has even symmetry. It's symmetric across the y-axis. If p is not an integer, but it's still rational, then we get our root-like functions, which include the inverses of our integer power functions. So that means we have functions like the square root of x, or the cube root of x, or x to the 2/3 power, or x to the 4/5 power. It's important to note here that if the denominator of p is even, then the function does not exist for negative values of x. So if I have x to the 1/2 power, then I can't plug in a negative value for x because there's no, in the real number system, square root of a negative number. Finally, if p is irrational, so say p is the square root of 2 or p is equal to pi, then the function follows the same patterns as before, but the extra restriction on these irrational powers is that x must be greater than or equal to 0. We can't plug in negative values of x. As you can see, this family covers a whole lot of different functions, but they all have some similar things in common. For instance, if p is positive, then the x-intercept of the function is equal to x is equal to 0. Also, if the numerator of p is even and the denominator of p is odd, then the function has even symmetry. But if the denominator is odd and the numerator is also odd, then the function has odd symmetry. The same thing with end behavior. If the numerator of p is even and the denominator is odd, then the function has end behavior that reflects even polynomials. If the denominator is odd of p and the numerator of p is odd as well, then the function follows the end behavior of odd polynomials. Now, I just mentioned that the denominator of p must be odd for these symmetries to hold. That's because if I have an even denominator of p, then I'm restricted to just positive or 0 values for x. And so those symmetries don't really hold the same way. But end behavior does hold, at least for 0 to positive infinity for x. Again, if p is negative, then we always have the vertical asymptote at x is equal to 0 and a horizontal asymptote at y is equal to 0. Domains and ranges for these functions is pretty straightforward. The domain for power functions where the denominator of p is even, or if p is irrational, is from 0 to positive infinity. If the denominator of p is odd, then the domain is all real numbers. If the denominator of p is odd and the numerator is even, or the other way around, If the numerator is odd and the denominator is even, then the range of the function is 0 to infinity. If both the numerator of p is odd and the denominator of p is odd, then the range is all real numbers. If p is irrational, then the range is from 0 to positive infinity. Now, I've been neglecting a so far in this discussion, that coefficient in front of x, but just for simplicity's sake, because a acts like any other leading coefficient that we've been discussing so far. It dilates the function, either stretches or squishes the function, as well as if a is negative, that represents a vertical reflection across the x-axis for the function. And of course, if we have this vertical reflection, that is going to be reflected in the range of the function. In the next episode, we'll be tackling this problem. Find the function that passes through the point 27,6 and 125,10, and then prove that the function is odd, that it has odd symmetry. Try it out yourself, and I'll see you in the solution.